Hi, everyone. Okay. All right, there are 10 people watching. Let's just wait another minute. Let me know if the sound is okay. It should be. Hi, everyone. Okay, let's begin here. 10 people. I do leave these up, but it's kind of nice to have some real-time interaction here. Today's lab, virtual lab, is on magnetism. And that's actually going to be next week's topic. Maybe I should just say a little bit about what's remaining in the course. There's not much left. There's magnetism. I'm going to guess maybe an hour and a half of lecture or video lecture, and optics, which is probably another hour, and then we're done. And for the rest of the semester, I'll just do live streams and do problems with people to get ready for the final. But let's do this lab now. Magnetism, it's lab number 10, which is this one right here. So open that up in a new tab, and we'll look at that in a second. And as usual, way down at the bottom here, I have basically a summary of what I expect to see in this lab, and also some YouTube videos uh, describing the phenomena that we're going to look at. Okay, so let's switch over to the lab write-up, and there's actually two things that we're really going to be doing today. Okay, the first one is to show the relationship between electricity and magnetism. Basically, that is that magnetism, it really is electricity, but in disguise. A static charge does not produce a magnetic field. Okay, and if you go back to my first lecture on electricity and magnetism, I actually said, look, if you have a compass, which is just a magnet on a swivel, and you put a charge beside it, a positive or negative, it will not turn the magnet. It won't have any force on the magnet. And the magnet's made out of a north and a south pole, and charges, of course, are positive and negative. And so a positive charge neither attracts nor repels the north pole. It neither attracts nor repels the south pole, and the same thing for a negative charge. But what Ørsted discovered, and then Ampere actually formalized with his law known as Amperes Law, is it's not static charges, but it's moving charges. Okay, and moving charges actually produce magnetic fields. And so that's the first thing we're going to show. So we're going to show that moving charges will actually generate a magnetic field. The second thing is, now that you've got this thing called a magnetic field, what does it do? Does it exert a force on static charges? And the answer is no. What a magnetic field actually exerts a force on is moving charges. So that seems a little strange. Magnetic fields come out of currents. Moving charges, a moving charge is a current. Okay, so magnetic fields are generated by currents, and magnetic fields exert forces on currents. And that's the second thing we're going to show, and that's known as Lorentz's law. Okay, so let's start off with Ampere's law. How does a wire create a magnetic field? And you can actually see a picture here in the diagram, and what you have there is in the middle here you have this wire. Okay, this straight wire, and it's carrying a current. And we came up with this convention that current flows from positive to negative before we even knew about electrons. And so this is actually, this arrow is actually pointing from the positive side of the battery, which would be down here. Okay, so the battery's not shown in this circuit diagram, but you would have like the positive side of the battery here and the negative side of the battery here. Or if we were doing this in the lab, we would actually use a power supply. Okay, and as the current flows, it actually generates this magnetic field, and the magnetic field actually circulates around the wire. So this is kind of different. Okay, it's not an electric field; it circulates around the wire. And I'll give you the formula for it in a second. But if you say, well, how does it circulate around the wire? You can actually get the direction by taking your right hand. This is a right hand rule over here, and you point your thumb in the direction of the current, and that is the current traveling from positive to negative, and your fingers point in the direction of the magnetic field. Okay, so the magnetic field actually circulates around this current like that. All right, and the wire itself, it's not positive or negative, it's actually charge neutral. So there's just as many, like in any segment, there's just as many protons as there are electrons, so it's charge neutral. So it's not static electricity that's causing this. It's actually the fact that there are charges that are moving inside this wire. Okay, and that gives rise to a magnetic field. So one of the YouTube videos I have will actually demonstrate this using a compass. Okay, it's not exactly a compass; it's just a magnet on a swivel, which is really what a compass is. And you'll see that when he turns on the magnetic field, the compass just flips and aligns itself right along the field lines. Okay, now in the lab you would have done that, and actually Ampere's law. Well, here's maybe I should just show you. This diagram is an attempt to show you how the right-hand rule works. Okay, so basically your thumb would point in the direction of the current, and your fingers actually point in the direction of the magnetic field. So you see this magnetic field is actually circulating around the wire. Okay, now the magnetic field in intensity decreases as you go further out from the wire. Okay, and you can actually measure this using an instrument known as a Gauss meter, but you can even just see the fact that it's circulating by moving the compass around the wire. Now, at a distance r from the wire, you're going to have a magnetic field, which is actually inversely proportional to r, and this is what Ampere discovered. So Ørsted first discovered the phenomenon that a wire will actually produce a magnetic field, but Ampere actually came up with Ampere's law, and what he discovered was that if you just take the magnetic field and you multiply it by a little delta L and you just sum that all up all around the wire, it's just equal to the current going through that wire, going through that loop that you made. So this is actually like a calculus thing, and I don't want to get into the calculus here. It's an integral around the wire, but basically all you have to understand it is you could just take, like, I think there's a diagram. No, it's this diagram here, like that. Yeah, it's this diagram right here. Okay, you could just take like little segments of the loop. Okay, those are like your little delta L's, and you multiply delta L by B, and you just add them up. You add up B times delta L B plus times delta L B plus B times delta L plus B times delta L, and you add them all the way up, all the way around that, and you know what it's equal to? It's equal to the current going through the wire. Okay, well, not quite. It's equal to the current going through the wire multiplied by this constant right here, and that's mu naught. Okay, and if you've been following my lectures on electricity and magnetism, you know that there's this epsilon naught, which comes up in capacitors. That's the permittivity of free space. This one, and that's for electric fields. This one is called the permeability of free space, and it's for magnetic fields. And if you confuse permittivity and permeability, the two names, everyone does. I don't know why they came up with these two names, but basically epsilon naught is the ability of free space or empty space to sustain magnetic fields, and mu naught is the ability of empty space, a vacuum, to sustain magnetic fields. Well, this is one way you can look. This is a more general way of looking at Ampere's law, but if you apply it to a wire, and you just go around a circle, well, going around a circle, that's a distance 2 pi at a radius r. That's a circumference of 2 pi r, so that delta L part just adds up to 2 pi r, and you get this equation here: B is equal to mu naught I 2 pi over r. Okay, in the lab, what you would have done is you would have taken a wire and attached it to a power supply, and you would have done two things. One thing that you would have done is just moved the compass around it, and what you would have discovered is that the compass points with its north pole always along the field lines. So let me just go back to this diagram for a second here. You see these lines there, like the B is pointing, like I guess to our right here. If you put a compass there, north would actually point along in the same direction as the B field. Okay, and the intensity of it, that's a little harder to do. You would use this instrument known as a Gauss meter, which I'll describe a little bit in a second. But with the Gauss meter, you'd actually be able to measure the B field, and then you would know the current, because after all, you're setting it on the power supply. You know the radius, because you know how far from the wire you're actually measuring it, and mu naught is a constant, which you can look up. Okay, and 2 pi is a constant as well, and you could actually show that this is verified. Let me look in the chat and see if there's any questions. There are no questions in the chat. Okay, so there we go. Whoops, and I lost my... All right, there we go. Okay, so we're back. All right, well, there's the story with the wire. We're still on Ampere's law. A better way to actually show that Ampere's law works is not with a wire, a straight wire, but a wire which is looped over and over and over again. Okay, now the more loops you have, that's like more current that you're putting in the same region of space. Okay, why? Well, because if you got one loop, then you have like one eye. But imagine you had a wire right beside it and it's also carrying a current eye. And then a third one and a fourth one. Every time you make a loop, it's like you're increasing the current and you would actually create a stronger and stronger magnetic field. It's like multiplying I um, by n, which is n is the number of times number of turns that you made. Okay, now it's impossible to just keep putting the same loop in the same place. Okay, so actually what we do is we take a wire and we just loop it and we coil it. We create like a coil, kind of like a slinky. Okay, and this thing is actually called a solenoid, and there should be a picture of a solenoid down here. Well, there's the picture of the loop. And I don't think he has a picture of a solenoid. I should have gotten a picture of a solenoid. Well, there's a schematic picture of a solenoid. It's good enough for our purposes. Okay, you will definitely see you'll definitely see a solenoid in I guess the second or the third YouTube video. But basically, it's a coil of wire. And one of the things that happens with the solenoid is the magnetic field is actually contained within the loops here. So you see these are all loops of wires, so lots of loops, like a slinky. Okay, and you put this current through these loops of wires, and if you apply the right hand rule, okay, like this, all right, you say, well, now which way would I point my thumb? Well, you would point your thumb in the direction, you could sort of see it here in this diagram. You point your thumb in the direction of the loop, and your hand is kind of going inside the loop. Okay, and so what happens is each one of the loops in the slinky is actually producing a B field, and then the next one is producing another B field, and it's another B, and they all add up inside the solenoid, and that creates quite a big B field inside the solenoid. Okay, you can actually make it even bigger by putting something in there like iron, and then if you have all these loops of wire around the iron, you've basically made an electromagnet. Okay, and when you apply a current to that, the amount of magnetic field that's actually induced inside the iron can be pretty big, enough that you've seen probably in movies where cars can be picked up by electromagnets, so they can be quite powerful. Okay, so if this number 3, equation 3 here, is the formula for a single wire, the magnetic field of a single wire at a distance r. So the wire's carrying a current I, and you're at a distance r from the wire, then you would get a magnetic field B like that. Okay, but what if you have one of these solenoids? All right, and that's actually described in the previous paragraph. It just says what I just described. So now what you have is you have a solenoid, and there's a couple of geometrical considerations about the solenoid. The first one is capital N. Okay, and that's just the number of times you've wrapped this thing. Okay, so the more times you wrap it, the more magnetic field you get. In fact, you expect that, because if you have n windings, n times I is going to be the amount of current that's going around in a circle. Okay, and so the B field is going to scale as not only your current, but also the number of wraps that your solenoid is made. There's another one, and that's L there. So there's another property that goes in here, and that's the length. Because if you're able to get the windings in a really, really tight space, then you're going to get a lot of B field. But if you spread that out over distance L, like that, little l here is the length of the solenoid, then you're actually going to decrease the magnetic field. Okay, so the magnetic field in a solenoid goes as the current. As you keep increasing the current, you're going to get more and more magnetic field. If you have more windings, more turns in the solenoid, you're going to increase the B field. But the more you spread it out, the smaller the B field is going to be. Or the other way to put it is, if the more you compact the windings, the more you're going to get, the bigger magnetic field you're going to get. Okay, this is still Ampere's law, and you can actually prove this. It requires calculus, so I'm not, I'm not going to do that, and Dr. DeHaven doesn't do it. But there it is. And actually, in one of the videos, there's a qualitative demonstration of what the B field looks like. And the guy just takes a compass and he moves it around the solenoid. And you see that in the solenoid, the B field actually passes through the middle of the coil, but then it kind of wraps when it comes out the one of the holes or one of the ends, it kind of flares out and then wraps in through the other side. Okay, and you can actually see that because the compass is moved around. Okay, now we're not going to verify this formula here. This formula, even in the lab, it's very hard to do, and I have yet to describe how that Gauss meter works. That's very hard to do, but this one is pretty easy to do in the lab. Okay. And so I have another video where they actually did the experiment, and they get a couple of numbers and they give you all the numbers. And so I even tell you the timestamp. It's at the 5-minute mark. If you go to the 5-minute mark, you can watch all of it and you can see them setting it up. But when you get to the 5-minute mark, you can actually see the numbers where they have the current. They'll tell you the number of windings. They tell you the length of it, and they get the current. And then they use this Gauss meter to measure the magnetic field. And there's a couple of values there. It's not a lot. They didn't do all of it because I guess they expected the students to do more of it. And so there's only a couple of values. But at least for those couple of values, you can use this formula and see, does it work? Does it work out? Okay. There's one thing I got to tell you about that video. It's not in English. Yeah, I'm not sure if it's in Arabic or Farsi, but it doesn't matter. Okay. You don't have to watch it very carefully. I picked it out because if you just watch them, you can watch these videos even at like 1.5 speed or twice speed. You could just see them setting it up, and that's all you really need to see. Is you need to see them setting it up and getting everything together. And then when you get to the 5-minute mark, you'll actually see the numbers there, and you can use those and see if this formula actually works out. Okay. Now a couple of more things before I go on to the next part of the lab. The Gauss meter is actually a device which is used to measure magnetic fields. Okay, and they're very sensitive. And you'll see in my very first video, I actually show you a Gauss meter, and the person that's using it, I don't think they fully understand magnetism, but that's not the important thing. The important thing that I want you to notice is that when they put the probe near the magnetic field, there's a lot of fluctuation in the numbers. Okay, and they're measuring it first in milliteslas, and then they switch to Gausses, and you wonder, why is there's this huge fluctuation? And here's the thing: the Gauss meter is super sensitive to the orientation of the probe. Okay, so if you have magnetic fields that are traveling this way, the probe, it's actually flat. Okay, and there was yet another video, I didn't give it to you, but you could actually see the flatness of the probe. In this particular video you can't, but the probe is actually flat, and if you orient it so that the magnetic field, it's actually perpendicular to the flat surface, that's when you get the maximum value. But you turn it just a little bit one way or the other, and you're going to get very different readings. If you have it like this, actually, so that this is the probe is flat like that and the magnetic field's like that, you actually get a measurement of 0. And if it's like that, that's when you get your maximum measurement. Okay, so you'll notice that when this person is putting the Gauss meter up against these magnets, you get this wild fluctuation. Okay, and you would have actually seen that in the lab as well. Okay, so when you take this Gauss meter and you try to measure like these magnetic fields, and these magnetic fields are already turning around, they're rotating around the wire, it's kind of really tricky to get the right value. Okay, it's very easy to get much less than the maximum value because all you have to do is just turn it a little bit, and then it doesn't quite work as well. Okay, but with the solenoid, it's actually very easy to measure, to orient it correctly, because in the solenoid, if this is the solenoid like this, the magnetic field is completely axial. It's right down the middle of the, so here's the solenoid like this, and it's the magnetic field goes straight through the middle of it. And so if you put your Gauss meter there perpendicular to one of the mouths of the solenoid, you get an excellent reading. Okay, so they do that in that one lab, and you can actually see if this formula works out. Okay, last thing about magnetic fields: what are the units of magnetic fields? The units of magnetic field, the MKS unit is a Tesla. A Tesla is a very big unit. Okay, I mean, I don't know what the Earth's magnetic field is, but it's only a few milliteslas. Okay, if you want to get up into the Tesla range, things like like the MRIs that they use for uh, imaging of like the brain or whatever, they get up into several Teslas. Okay, so those are really, really big electromagnets. But generally speaking, magnetism in the lab is in the millitesla range. Okay, a good magnet might get up into the few hundreds of milliteslas, but a full Tesla is pretty darn big. Okay, so okay, there you go. There's the theory for Ampere's law. Okay, and let's go on to the second point in the lab. And the second point in the lab is what's known as the Lorentz force. Okay, and I guess we can look at this diagram first. All right. Um, remember I started off telling you that um, electric currents produce magnetic fields, and at the same time, magnetic fields exert forces on electric currents. Actually, let me look in the lab, in the chat here. There are no questions. Okay, all right, so let me go on. Well, if you have a magnetic field here, and you can see here all these straight lines, these horizontal lines here, okay, those horizontal lines, they're like the magnetic field, say, inside of a solenoid, all right? So inside of a solenoid, the magnetic field is uniform, and it's all in the same direction, so it's very nice for doing experiments. And then what you do is you take a wire, and here's my wire, and this wire simply cuts across the magnetic field like that. Okay, now there's a few things to note here. If the magnetic field is not infinite in size, okay, it has some length. Notice that it's a length L, little L here. That's the length of the wire that is bathed within the magnetic field. Okay, the second thing to note is this angle theta. Okay, so notice that the wire isn't necessarily perpendicular to the magnetic field. That's when you would get maximum. Or it's not parallel to the magnetic field. That's when you would get zero. Okay, it's at some angle theta. And it's carrying a current I. Okay, if you have those three things, so the length of the wire within the magnetic field, like the wire could be very long, but only a length L, little L, that's the part of the wire that's within the magnetic field, and it's cutting the magnetic field at an angle theta, and it's carrying a current I, then the force on that wire is given by this formula here. Okay, and this is known as the Lorentz force, named after a physicist called Lorentz who discovered it. And basically, the force increases as you increase I. So the more current you put through the wire, the more force there's going to be. The second one is that the more of the wire is bathed within the field, the more force there's going to be. It's kind of like a force per unit length. The bigger the magnetic field itself, the more force there's going to be. And then there's this sine theta. Okay, and this is interesting because if theta is 90 degrees, that's when you get your maximum. Okay, and that happens when the length of the wire is actually perpendicular to the magnetic field. So if we go back to this diagram, if this wire were straight up and down like that, okay, vertical, if the wire were vertical and the magnetic field is horizontal like that, that's when the theta would be 90 degrees, and that's when you get your maximum force. Okay. Conversely, if the wire is directly along the magnetic field lines, theta would be zero, and you would get no force at all. All right. So this is kind of interesting, because what it means is that the force, the magnetic field, it doesn't work like, remember, an electric field, it'll accelerate a charged particle in the direction of the electric field, or in the opposite direction if it's a negatively charged particle. But there, with the electric field, it's collinear with the field lines, but not here. Here, it's actually when it's perpendicular that you actually get the most force. And here's where it gets even crazier. The force is actually out of the page. Okay, so if you were, well, it depends. It depends on which way the current is going. So I should be careful. If the current is going from the bottom of the page to the top, well, then it would actually be into the page. Okay, and if the current were going the other way, it'd be actually out of the page. And so this is kind of crazy because basically the force is perpendicular to both the field lines and the current. Okay, and so that's kind of different. All right, and you'll see that in my last video. Okay, and I'll describe that in a second, but let's finish off with the Lorentz force here. You're going to have this force, and if you're going to actually do perpendicular, and in the experiment that you would have done in the lab, and also in the experiment that you're going to see in the YouTube video, you would have put the wire perpendicular to the field line. So you would have had the solenoid like this, okay? And then you would have actually had a wire at the edge of the solenoid perpendicular to it, and you would actually be able to measure the the force on it, okay? And well, there it is. All right. So experimentally, what you would have done for the first one is you would have had this solenoid. I guess I should scroll down here. Experimentally, there, yeah, there's the Gauss meter. Okay, the probe of the Gauss meter. And what you would have done for the first one is you would have had the solenoid, you would have applied a current, and you would have put the Gauss meter in there, and you would have measured how many Gausses of um, uh, sorry, how many milliteslas of magnetic field do you get per amp? Okay, and you would have then verified that formula. Well, we're not going to do that. You're going to look at that YouTube video and use those two values. For the second part, which is the Lorentz Force, it would have been even more difficult. What you basically do there is you would have used this thing called it's just basically like a balance, okay? And what you can't see here is because you're looking at it on end, but there's basically a wire which is traveling into the page here, so you can't see it. So because that wire is into the page, remember the magnetic field is like linear here. So this is the solenoid, the edges of the solenoid right there. Okay, those are the edges of the solenoid. So it's kind of a cross section of the cylinder. Okay, and then you would have had a wire, and this wire would have actually gone into the page. Okay, it was on. It's like on a. I don't know. It's mounted on this ceramic um, platform, and you would have put a current through it. And when you put the current through it, there would have been a force down, which would have lifted this end, and then you would have put a little mass here to balance it. And by knowing how big that mass is, you would have been able to calculate that force there like that. That's actually not how it's done in the video that I found online. It's actually a much better experiment what they did online. They simply took a wire between two magnets, and they were able to show, and they put that on top of a balance, like a balance which just measures weight. And what they were able to show is as they turn on the current, there'll be so much force down, and you can actually see that on the balance. And as you double the current, it'll double the force down. They triple the current, and they'll triple the force down. Now, in that part of the lab, you are trying to verify this equation here. You are trying to verify this equation here, but you don't have the numbers, and there are no numbers there. Okay, so unlike, if we had actually done the lab physically, you would have had those numbers. You don't. But here's what you do have. They show you that the force increases linearly with I. So I think they set it to 1 amp, and then they measure the force. And then they set it to 2 amps, and they measure the force. And they set it to 3 amps, and they measure the force. And guess what this formula predicts? This formula predicts that as you increase I linearly, the current linearly, you should get linear increase in the force. And in fact, that does show up. So, even though you're not totally proving this equation, at the very least, you're showing that there is a linear relationship between the current and the Lorentz force, okay? And the magnetic field there is actually not even produced by a solenoid. It's just 2-bar magnets. And you don't need to use a solenoid to create the magnetism. Any source of magnetic field gives you a B, and you put a current through that, and you're going to get a force. And it also shows that the force is actually perpendicular to the B field, because the wire is going this way in the video. The B field is going between the two magnets this way, and the force is actually down. Okay. Last thing I'll say about the Lorentz force. This is actually what describes like the aurora borealis, the northern lights. Those are charged particles that get trapped in the Earth's magnetic field. And in the Earth's magnetic field, if the field lines, say the field lines are going up and down like this, so B is going, say, up, okay? And a charged particle is going this way like that, okay, towards you guys, all right? The force is actually going to be either to the left or to the right, depending on whether it's a positively charged particle or negatively charged particle. So let's think about this. So the particle's moving that way. The field is up, but the force is that way. Well, if it's moving that way and the force is that way, it's going to turn. But now that it's turned it, it's also going to turn the force, and it's going to turn it. The force is always going to be perpendicular to the velocity. In other words, the acceleration is always going to be perpendicular to the velocity. In other words, you're going to get uniform circular motion. And that's exactly what happens when you inject charged particles into a magnetic field. They'll go in like this, so this is this charged particle coming towards you, but it feels a force that way, and so it starts to turn and turn and turn and turn and turn like that. Okay, and because of the shape of the magnetic field at the north and south pole, not only will it turn, but it's got a slight curvature inwards. It'll actually be pulled into kind of a spiral, and these charged particles, they spiral into our atmosphere, and they make our atmosphere glow, and you get the northern lights or the southern lights if you're in the south pole. Okay, so that's enough for the theory. Let me see if there's any questions in the chat. You guys are pretty quiet. I guess everyone's understanding what I'm saying. So let me just show you what I expect for a lab write-up from this. Okay, let me go over here. And let's look at the summary. Oh, so maybe I should show you where that is. So if you just, our Moodle site here, go all the way to the bottom. It says summary of the lab. And if you click on summary of the lab, um, there we go. So let's go through this. Oh, let me scroll down a bit here like that. So the first thing is in your introduction section, like always, try to always be concise but complete. Okay, what are you trying to do in this lab? Like, what was the purpose of it? And as I said, there are really two purposes of it. One is to demonstrate Ampere's law, and the other one is to demonstrate the Lorentz force. Okay, so for number one, the Ampere's law, you're going to show that a wire carrying a current creates a magnetic field. Okay, that is a qualitative statement of Ampere's law. A wire carrying a current produces a magnetic field, and we're going to show it for two cases: the straight wire, okay, and there we just show it qualitatively because you're going to get a magnet. The video, you're going to see someone move a compass around the wire, and you'll see that, well, not quite move a compass around the wire, but you'll see the wire actually turn a compass needle, okay? And the other one is you're going to do it for a coiled wire, in other words, for a solenoid, okay? And so that's Ampere's law. So that's one thing that you're trying to demonstrate with this lab. And the other one is to show that a magnetic field exerts a force on a wire carrying a current. Okay, and that's known as the Lorentz force, and that's the last video. All right, so for the experimental, what do I want you to do? Well, I want you to, watch the very first video, which is on how to use a Gauss meter. There's other videos online on how to use Gauss meters. They're more technical. You don't really need something terribly technical, but what I did like about this one, even though the person, I don't know if they understood how Gauss meters work or not, but you'll notice is that as they're moving this like probe around, they've got a magnet, and they move the probe, and boy, the numbers will just fluctuate all over the place. And the reason being is that they're not, you have to orient it correctly. They do at one point say, find the sweet spot. And what they mean by the sweet spot is you've actually got the probe's head, perpendicular to the field lines. Okay, so that, and then also what units are used for in a Gauss meter. So remember, a Tesla is the MKS unit. Okay, and most Gauss meters will measure in two different units: milliteslas, which are thousands of a Tesla, and then this other unit called a Gauss. Okay, and it's kind of a traditional unit, and it's stuck with us. And basically, it's 1 millitesla is just equal to 10 Gauss. I don't know its history, but a lot of people tend to measure magnetic fields in Gauss rather than milliteslas. But it's not even it's not anything very deep. It's just that 1 millitesla is like 10 Gauss. Okay, all right. So that's one, and then the other one is I want you to watch the. This is still in the experimental. Watch the very last video, which shows how the Lorentz force, that demonstrates the Lorentz force. Describe that experimental setup, because that experimental setup is different than the one that Dr. DeHaven has in his lab write-up, okay? Personally, I think the one that you see in that video is much better. If I were to do this lab in the future, I think I'm going to scrap that one and just adopt the technique that was used in that YouTube video. It's just there's no reason to use a solenoid to create the magnetic field. You just already have two magnets, or you could use a horseshoe magnet. You measure the magnetic field using a Gauss meter in there, and then you just have a wire and you measure the force on the wire using a balance, something like we did in the Archimedes lab, where you just measure how heavy something is. And like they're measuring with 1 amp, the guy was measuring zero point 0.3 grams, and zero point 0.3 grams is, for some of these very sensitive balances, that's enough to give you a number to work to see if to verify Lorenz's the equation for the Lorentz force. Okay, so back to this. This is still in the experimental. Just describe the experimental setup, and then in your results section, watch the YouTube videos. Whoops, watch the YouTube videos, but also describe what you see in them. Okay, and so there's one where they look at the B field around the wire and the B field around the solenoid, just the shape. Okay, so there's a couple there which are just qualitatively, what's the shape? And then there's another one, this is that third one that's not in English, okay, so I do mention that there, where if you go to the 5-minute mark, you actually will see a couple of numbers there. And they give you the values for the number of windings, N, the length of the solenoid, L, the current, because they set it on the power supply, and they measure the magnetic field using a Gauss meter. And I didn't actually do the calculations, but looking at the numbers, they look approximately right. Okay, so we'll see how close they are. Okay, if they're not exactly right, well then that's fine too. But at least we'll see how close they are. So and so I'm asking you, do the calculations theoretically. Look at the numbers they got for the magnetic field. Do they agree or not? Are they at least in the right ballpark? Do they agree? Okay, and so on. And then the last one, watch the last video, and that's the one that demonstrates the Lorentz force. So in the experimental section, you just describe the apparatus. In the results section, what did you see? And you really didn't prove the full Lorentz force, but it does at least show that the force is proportional to the current. Okay, and then finally a discussion, just summarizing that. And one of the nice things that you can add in these discussions is how could you do better? It's very frustrating for me to try to find YouTube videos that do it just right. A lot of these videos are kind of I just didn't have time to produce good videos for the lab, and I could have done a better job. But you can look at these videos and go, well, they could have done a better job here. So you can put that in your discussion. Okay, so that's it for the lab on magnetism. Let me see if there's any questions in the chat. I'm not seeing any questions in the chat. There are 9 people watching. I wonder who's not watching. Okay, so I'll just wait a few seconds. If there are no questions, we're fine. Do people know what you have to do for this? Or if you have any other questions for any of the previous labs, because now's a good time to ask questions. I'm getting just silence here. All right, not seeing any questions. You can always ask. Yeah, you can always ask questions at any time. So one of the things that I have these 7 o'clock Google Hangouts. If you guys have questions at any time, you can either email them to me, or creating a Google Hangout takes no time at all. If you email me and say, yeah, you want to just um, you know jump into a Google Hangout, we can do that too. But okay, I'm getting a bunch of all good. So you know what? Let's call it a lab, and well, there it is. Okay, we'll see you next week in our virtual lab. Bye bye.